Let me see if I see any hands. Don't seem to be. Well, I guess if anybody wants to ask something, please go ahead, unmute yourself. And James Nakamura, please go ahead.
Hi. So one thing
Hi.
you thank you for the talk. And at the 5-half state, you mentioned that low temperature below 25 millikelvin, the RXX was no longer 0.
So it was 30 millikelvin that I started seeing, okay, so if you, I don't know how much affects the kind of experiment you do. For us, even if it is 10 ohms, I don't want to take the chance because, I'm measuring a very small number, and the more compromises I do, the more error I incorporate in the measurements. And that's the reason that I stopped measuring when I knew that my RXX is not purely 0. Yeah. So, but the gap is 240 millikelvin for the sample, 220 to 240. Yeah.
Do you know why it increases with lowering temperature?
Okay. So this is what Dima was talking about, is that our expectation is that there is not enough equilibration, like as you go at high temperature. I also showed you for the data for 2/3, right? So when we were increasing the temperature, you are somehow helping them to equilibrate. But when we are going to lower and lower temperature, then all these edge modes, they need to be mediated by something, right? When you are expecting them to equilibrate.
I'm sorry, are you talking about the heat or the electrical conductivity now? I think there's a confusion here.
Okay. No, electrical conductivity was always quantized and perfect. There was no problem.
Until above 3, you say it breaks down at high temperatures. You're saying
It's like if the 5F will be staying until 200. This is why I said 240 Kelvin, because we like the 5F quantization stays up to almost 150, 200, I think is something like this I measured. Yeah. But that plateau was present, that plateau was quantized, but the RXX started being, 1 ohm, 10 ohm, and then it was like going up slowly. Yeah.
Okay, thank
you. That's what I mean.
James, do you still have a question? Your hands is still up. Not. Okay, Gabor, please.
Hi, Mitali. Very nice talk.
Hi. You heard it so many times.
Yes. I wanted to ask you some technical detail. So
yes, please.
How do you do the measurement? So with your voltage amplifier, you're gonna measure a voltage fluctuation. So then to transform that into a current fluctuation, you're gonna need an impedance. And so presumably you plug in your sample impedance, and then you have the impedance of the resonator.
Yes.
So
exactly.
What kind of equivalent resistance, for example, do you have for your LC circuit?
So the thing is that for our LC, the L is a superconducting circuit, So the thing is that it has a very small series resistance. So when you are in the parallel, it's a huge number. So I can always take my quantum pot.
So
yeah, it's a superconducting circuit. That's the thing.
Cable is also like superconducting that goes to the amplifier.
No. So the cable that goes from from sample, I have a coax that goes to the LC circuit. So that is the C that I'm talking about. I don't have any extra C. The C that I'm talking here is just the coax that goes from the sample output to the input, your LC circuit, just to have the to be connected there. So that is my C, and the R is my edge, and the L is superconductor. That's the circuit.
But presumably, if you have a resistance in the cable, that's still going to give you an equivalent resistance.
So so the thing is that if I have a resistance which is very high, let's say even if I 10 kilo ohm, and let's say I have only, are you talking about the fact that the resistance of this, the C that the line that is going, that the coax that is going, right? So this is a meter, not even meter, it's like 30 centimeter of a line, because that's my cold finger. So it's really not much. Yeah.
Okay. All right. Well, thank you.
Sure. Welcome.
Son, you have a hand up, so please go ahead.
Yeah. So in this experiment with the interface, can you rule out the Fafian?
So basically, I think Moti will be a good person to talk here, because I should not trespass their interest. Moti is here. I think he was here.
Yes, I'm here. I can comment. Thanks first of all, thank Mitali for the short advertisement of the work that we just measured last week. I assume, Don, you talk about the last transparency that we are facing, right?
Yes.
Okay, so the Pafian was never really a problem because it doesn't have an upstream mode. Okay, so we always measure from years ago that we have an upstream neutral mode. The Pafian was not there. Only if there is some unexpected reconstruction of the surface or things like this. But the paper that Mitali mentioned that appeared on the archive a few months ago suggests that maybe also something like this exists if you have some funny edge reconstruction, which we don't see when we look at 8/3 and 7/3, because there we know the kappa, we know the thermal conductors, okay? So this particular experiment that is now flashed upon here, the previous one looked only on neutral mode direction. This particular one measured the actual kappa of the half mode plus the Majorana. And the nice thing about it is that the anti-Pafian is all equilibrated to begin with. There's no issue at all. So if it's anti-Pafian, you get now 1.5 kappa 0, full stop. The pH Pafian must be equilibrated. And it's interesting that the distance of 150 microns, BIVAS measure 0.5, exactly what you expect for the pH Pafian. So the nice thing here that you throw away all the integer, you look only on the Majorana and the half edge. Is this answering your question?
Yeah, thank you very much. Yeah, it's very nice.
Thank you.
Any other questions?
If not, I can stop sharing my screen, maybe.
We still have about 7 minutes, I guess, until the next session officially should start. So I don't know. Andrei, do you think we should wait till then? I guess normally we would, right? Because other people may want to join.
Yeah. Let's wait until the next session starts. In the meantime, if some of you suddenly think of a question, feel free to speak up.
Right.
Maybe I can add also one more thing is for Dima. Dima, can you hear me?
Yes, I can.
Okay, so as you say, the pH Pafian is supposed to be terribly equilibrated, but you see that in this last data that you don't know yet about, that's the one that Mitali flashed last Thursday, 150 microns was totally sufficient for this, and we know from the previous paper in the archive that the integer do nothing anyhow.
Right. That's what we argued with scans, that integers should not affect the equilibration length, and you would get, but so at what temperature did you get the 0.5?
It's about 10 to 12.
Oh, so it's much better equilibrated than any previous sample. That's interesting. So maybe your interface is doing something. Maybe it increases disorder. That should help equilibration.
Yeah, I think that it's very, you mentioned also some graphene work that came from India, I suppose. Right, but this is I think it's well, you know, the distances they talk about there is 4 microns. So it's very
It's
difficult.
6,
4
yeah,
microns.
6, yeah, 4.
Right,
Yeah,
right. The distance is some 5 micron. So they, of course, are
Yeah, so it's
applicable.
impossible to say when you see nothing happening 4 microns to say that this is the long equilibration length by looking on the error bars or something like this. I think it's ridiculous in a way. But also at these 4 microns, you can have edge reconstruction and who the hell knows what.
Right, but what's curious about the data, I agree that one can tell that perhaps there is edge reconstruction, but curiously they get exactly the thermal conductance one expects when there is no edge reconstruction and no equilibration. So and given how short their sample is, it's tempting to think that that's what's going on. So of course there is no edge reconstruction is an interesting question. And I think that's a question that also applies to the anion collider experiment. So your samples like that would show edge reconstruction. Why that sample didn't?
Which one, the graphene or the
anion collider experiment?
The collider experiment, I'm not sure if there is no edge reconstruction. They looked for, and maybe I can get, if Gondel is on the line, he can respond, but I look carefully in the way they measured neutral modes, okay? They don't know if the edge reconstruction, they measure neutral modes, and I'm not convinced that they don't have neutral modes at all. I'm not convinced from the paper, from the supplementary part of the paper, but maybe it can be convinced by somebody. Anyhow, we saw edge reconstruction, which I will give tomorrow a talk, not on thermal. I'll give a talk tomorrow on many edge, on measuring short noise. Every time, every edge has reconstruction. I didn't find any except high integers that are not reconstruction, that are not at neutral mode. Neutral mode always exists at every time, every place we measure.
Well, but coming back to the experiment in India, that's graphene. So presumably edge reconstruction works in a very different way. So perhaps
yes,
that's not a big surprise that they don't see it.
Yeah, that's true. The edge might be very sharp. Yeah, that's true. Sure.
I think graphene edge is very sharp because Benjamin Sesepe, he has some data in STM, and I hope he will publish soon. And he told me that it's really sharp. Its edge is really on the edge, like it's not like gallium arsenide. Yeah.
But I think what this discussion shows, it's very important to have not just one experiment, but a set of experiments with similar samples. Then you know, are your contacts good or not? Then you know if you have edge reconstruction or not. If there is just one isolated experiment on just one aspect of the data, but nothing else, then it's very hard to make sense.
You talk
I
about
see another raised hand.
So what I'm talking is that that's great that you have similar samples on which you measure everything, the charge, the upstream mode, the edge reconstruction. Then when you have any new data like thermal conductance, you can put this into context and you know what it proves and what it doesn't prove. And if there is just...
the reason Dima, we do it because you were part of our collaborator with us in the first experiment is because the theorist really didn't like the result, right? I think if Bert is around, he can vouch for it that he really hated to see the pH bucket.
Well,
so we kept thinking about how to prove it, and we kept doing more and more experiments. I think people are tired already from the work we do.
Moti, but honestly, I think the most convincing theoretical picture would be that you must have multiple states of the 16-fold way. So it's a little bit of a puzzle while you have always the same. Of course, your samples are relatively similar, but I would expect that when things are significantly changing the sample, you will see something else. For example, I would be very much surprised if it's the same state at the low densities, when it looks like the gap goes down, then it grows again, and maybe there is another state there. So yeah. I would think it's a different topological order. So I think the system is very
I see one more hands up. So maybe you can talk to your collaborators offline. So Song Yang, you have a question? Please go ahead.
Yes, I have a question for Mitali. This is actually from my friend Bill Fogler, who is watching through YouTube. The question is, why does the particle Hall Pfaffian have a range of expected results while the anti-Pfaffian doesn't?
Can you repeat me, please, the question once more?
Yeah. Why does the particle Hall Pfaffian have a range of expected results while the anti-Pfaffian doesn't? So
the range of expected results
from the interface experiment.
Okay. So in the interface experiment, look, all I can tell you from my understanding is that if we can always think of these anti-Pfaffian, if you will believe the people who think that it is like, mixture of Pfaffian and anti-Pfaffian, then this pH Pfaffian can be always thought of some, on the edge in a small region, things like that. But if we really completely think that it is not the case and we have only pH Pfaffian state, and then how the edge looks like. I mean, like we all of us are, kind of showing you. It's like everything goes in one direction, only the Majorana goes in other direction. And then if you have an interface with different filling factor, let's say 2 or 3, where you can gap out the integer, and then you are only left with Majorana and the fractional one, right? And there is only so many ways it can show up. And the clue about these measurements that we do for upstream noise is this, that, that's no, like when we are putting current, the current is only going to be taken by charge edge modes, right? So I cannot really put the current, and the current will be never taken by the neutral modes. So when we see that the current is going in a different direction, but we are measuring noise in the completely opposite direction, we looked for which configuration can really give upstream noise in this particular interface. Am I making sense to you? I just want to mention, I want to make sure if I'm making sense to you or not, but that's the picture that we think when we are talking about this upstream noise that is being measured here. The idea is to decouple the charge or the current flow and the noise from it completely, because we do not want to measure the noise in the direction of the current, which is taken by charge, but we are trying to look for a device or try to look for a way or a trick to somehow isolate that I know for sure that the current is not moving upstream, because that cannot be true, because I'm sourcing current and it's always going downstream. And now I'm looking for an interface, where the configuration is such that only for a certain, state, there will be upstream noise. And I would really say, I'm sorry I didn't put enough in my slides, because it's not my work, and as I said, I do not want to really take the charm away from the measurement. But if you are interested, please attend the talk in EPQHS. It's going to be entire talk about all these things.
Just a comment, then, so is you say why you ask them why is it pH Pfaffian? That's what you ask, right?
Yeah. The question.
So let's not forget we are experimentalists. I mean, you're supposed to.
But we are over time. I think we are over time. I think we are over time. Right. Yeah. But thank you so much for the opportunity, and
thanks,
have a nice
everybody.
day.
Thanks both speakers and the interesting discussion.